Hi everybody. So today I'd like to talk to you about projectile motion. This is for Physics 1103 and we're using Giancolli's textbook for algebra-based physics, Physics Principles with Applications. So projectile motion is motion in two dimensions. Now it's important to understand that once you move beyond one dimension, using those plus or minus signs isn't always going to be enough to fully describe the motion. For example, if your motion is in both x and y, then if you just said plus or minus to indicate the direction, you wouldn't know whether to assign that plus or minus to the x direction or the y direction or both. So what you have to do now is specify not only plus and minus for direction, but also whether you're talking about x motion or y motion. The good news is that we're still going to be interested in the same quantities. Specifically, we're going to be interested in displacement, velocity, and acceleration. What we develop here is going to serve as the basis for motion in future chapters. So in projectile motion, we're going to say that an object can move in both the x direction, which we'll call left-right, maybe east-west, north-south, but we're also going to consider the y direction, which we'll designate as the up and down direction in these examples. The motion left, right, and up, down, we're going to say is independent of each other. We can say this because we're going to neglect air resistance. So when we do this, the form of 2D motion that we're going to deal with is called projectile motion. Now, a projectile we're going to define as an object moving in two dimensions under the influence of Earth's gravity. When it does this, the motion is parabolic. In these two images, you can see that they've done time-lapse photography for a ball bearing bouncing on a table and for a basketball being shot towards a hoop. So you can see that even though we're neglecting air resistance here, which you're really not supposed to do, it's actually not a terrible approximation. These images look very much like parabolas, so you can see that these assumptions work under certain conditions. Now, if you were to take those stop motion photographs and turn it into more of a schematic, then you can look at what the x and the y motion looks like at each one of those snapshots. Now you can see that we're going to analyze the horizontal and the vertical motions separately. Specifically depicted in this figure, you can see two different possibilities for a trajectory. In trajectory 1, the object falls straight down off the side of the table. In other words, maybe it just drops straight down from that height of the table. In that case, it's going just straight down and it's a vertical fall. And we've already dealt with that kind of stuff in a previous lecture. In the second case, this ball is given a small horizontal push off the side of the table. That gives it an initial velocity in that x direction. Now it's important to understand that under projectile motion, the only acceleration that an object experiences once it's released is that acceleration due to gravity, which is going to act only in the y direction. Because we're neglecting air resistance here, there's no acceleration in the x direction. So the x direction experiences no acceleration, so that x velocity stays the same all throughout the motion of that path. In other words, whatever you give it at the beginning, that's the same x velocity that it's going to have there at the end. The y velocity, however, is going to change because it's falling under the influence of gravity. So you can see that that little ball launched to the side starts off with no y velocity, but as time goes on, that y velocity component gets larger and larger. So here's our assumptions. First, the effective air resistance is negligible. This is a very important one. Otherwise, you are going to have an acceleration in the x direction. It makes the problems way more complicated, and we're not going to deal with that in this algebra-based physics course. Second, the free fall acceleration is constant over the range of motion. So the acceleration, the only one that's working here, is the acceleration due to gravity, which is downward in the y direction only. And the magnitude of that acceleration is 9.8 meters per second squared. This is going to be a reasonable assumption as long as the range is small compared to the radius of the Earth, and we wouldn't give you anything more complex than that in an introductory algebra-based physics course. If you make these assumptions, then the object in the projectile motion is going to follow that parabolic path that I already mentioned, and I will refer to this path as a trajectory. Here's a little bit more complex example than that previous schematic. In this example, I've got some sort of object that maybe I've shot out of a cannon, maybe I've thrown it, it doesn't really matter why, but I've given it a velocity that initially has both an x and a y component. When I do this, I've got that initial x velocity component, and it's going to stay the same all throughout the trajectory of that particle because there is no acceleration acting on the particle in the x direction. So if you look at the x component of the velocity all throughout the path, the arrow is going to be the same length and point in the same direction for the x in each one of those little snapshots. The y direction, however, the velocity does change. You can see that because there's an acceleration downward, and I've given it an initial velocity that does have a y component in the upward direction here, what's happening is that the y component of the velocity starts off large and upwards. And then, since the acceleration due to gravity is pointing downwards, as it moves through the trajectory, the y component of the velocity goes down. When it reaches the top of that parabola, it's going to start turning around and falling downward. So it goes from going up to going down in the y direction. When that happens, then just for a split second, the velocity in the y direction has to be equal to 0. So at the top of the trajectory, the y velocity is 0. Then it turns around and it starts to go downwards. It starts off with a low y velocity, but because the acceleration due to gravity is now pointing in the same direction as the velocity, right, on the downward part, then it gets larger. So that means that it speeds up as it goes down. So that's what's happening with projectile motion. So this model, yet again, is the superposition of two motions. Superposition just means I've got two different things going on. Those two things are the motion of a particle under constant velocity in the horizontal direction and the motion of the particle under constant acceleration in the vertical direction. This corresponds to the free fall equations that we talked about in a previous lecture. The implications here are the y component of the velocity is 0 at the maximum height or top of that trajectory. That acceleration in the y direction stays the same throughout that trajectory. So let's review what equations you might have to deal with so that we can understand this y motion. These are the equations that you're going to use. It's the free fall equations that we've already gone over. Okay? So for the y direction, you've got three possibilities for equations to use. The velocity in the y direction will equal to the velocity in the y direction initially, or the initial y velocity, minus the acceleration times the time. The acceleration here is gt, okay? So we have vy is equal to vy naught minus gt. The minus sign is because that acceleration, 9.8 meters per second squared, points down. So you've got vy is equal to vy naught minus 9.8 meters per second squared times the time. That'll give you the equation that links the velocities and the time. The other equation that you're going to use is y is equal to y naught plus vy naught times t minus 1/2 gt squared. Y is the position of the particle at some later time t. Y naught is the initial position of the particle at t is equal to 0. T is, of course, the time at whatever later time you pick. G is 9.8 meters per second squared, and yet again t is time. So that explains the second equation that you can use. Finally, you can use an equation which eliminates time altogether from the y direction. That one says vy squared is equal to vy naught squared minus 2g times y minus y naught. Here the vy is the velocity at some later time t. Vy naught is the initial velocity. In both of these cases, vy squared and vy naught squared, you're going to square those velocities of the initial and the final velocities in y. Yet again, g is 9.8 meters per second squared. the sign of the acceleration is taken care of in this minus sign out front. So you're doing minus 2 times 9.8 meters per second squared. The minus sign is there because the acceleration is down. And then you have times y minus y naught, where y is the position at some later time, and y naught is the initial position at time t is equal to 0. So those are the equations that you're going to use for vertical motion. Now, the equation that you're going to use for horizontal motion are simplified. Because there's no acceleration in the x direction, the initial velocity in the x is equal to the final velocity in the x. So that's written here as vx is equal to vx naught. Because there's no acceleration in the x direction, we don't have any of those v squared equations like we do for the y. We just have that the initial and the final velocities in the x are the same. And that leaves only one other equation really that we can use, and that's that x is equal to x naught plus vx naught times t. Yet again, because there's no acceleration in the x direction, that whole at squared part of that equation goes away. So those are the two equations that we can use for the horizontal direction. Now there's certain steps that you're going to go through to solve projectile motion problems. The first step is read the problem carefully and choose the objects that you're going to analyze. It's very important to draw a diagram, and then on the diagram that you just chose, make sure to choose an origin and a coordinate system. Next, decide on what time interval you're looking at. Make sure that you use the time to connect your x equations with your y equations. So it's very important that when you're solving these, that you make sure the time interval that you're considering is the same for the x as the y. Sometimes these things will be linked, and I'll show you that in a minute. Make sure that the only time the object is moving, you've got it under that constant acceleration downward due to gravity of 9.8 meters per second squared. Make sure that you analyze your x and your y equations completely separately. You might even want to make two columns on your paper with an x heading and a y heading. Keep those things separate. Make sure that you list your known and your unknown quantities, right? Remember that your velocity in the x direction never changes. Make sure that you understand that if you're at the highest point in the trajectory, the y velocity is going to be 0. And then make a plan. Look at the equations that you've got, look at your knowns and unknowns, and plot a course for how you're going to get there. Sometimes you might have to do a couple of steps, right, to get to your final answer. Let me do an example problem for you. We'll do more examples in class and work problems together. This one is, a ball is thrown into the air with an initial velocity of 50 meters per second at a launch angle of 37 degrees to the horizontal. Find the total time the ball is in the air, which is called the time of flight. The total horizontal distance that's traveled, that's sometimes called the range, and the maximum height of your projectile. Okay, so very first step, let's draw ourselves a picture, let's choose a coordinate system, and let's make sure that we understand what's going on by identifying our knowns and our unknowns. So this is my little drawing, okay? Here I have my initial velocity, which is indicated here in the red, and it's at an initial angle to that x-axis. You can see here that the x and y initial velocities are broken out there into these little arrows, which are the components of the velocity vector. Okay, so that's my picture. I've also indicated that gravity is down here with this purple arrow, and it's pointing only in the y direction, and it's down. Okay? Now I'm going to list my knowns and my unknowns. Since I put my origin, that was my choice, right there at the start of where the particle is, then I'm going to put x naught equals y naught equals 0. So those are my initial positions in both the x and y direction. It starts at the origin, so they're both 0. Now, my final position in y at some later time t is 0, because it's going to start from the ground or whatever, and it's going to land back on the ground, right? So my later time, y is equal to 0. My initial velocities in the x and the y, I have to solve, right? Because I've been given my total velocity magnitude, which is 50 meters per second, but I'm also told that that is at an angle of 37 degrees to the horizontal. So my x component of my initial velocity is going to be 50 meters per second times the cosine of 37 degrees. When I solve for that, I get my initial velocity in the x is 39.9 meters per second. My y component of my initial velocity will be the initial velocity magnitude times the sine of 37 degrees. When I solve for that, I get 50 meters per second times the sine of 37 degrees gives me 30.1 meters per second. Just to beat a dead horse here, the acceleration in the x direction is 0, right? No acceleration in the x. And in the y direction, my acceleration is minus 9.8 meters per second squared. So that's everything that I know, right? And now I'm going to go through and solve for the things that I don't know. Okay, so the first thing that we want is the time of flight, t. That's an unknown, all right? Now your time of flight is always going to be dictated by your y motion, okay? How long it's in the air depends on what's going on in y. So we're going to look at our equations for the y direction. Since I know my initial position in y, my final position in y, my initial velocity in y, and my acceleration in y, then I can use the equation y is equal to y naught plus vy naught t plus 1/2 ayt squared and solve for what my time is, right? Because I know everything in this equation except for the time. Plugging in the variables into that equation, y and y naught are both 0. So I have 0 is equal to 0, right? Now, vy naught is 30.1 meters per second, right? And then I have times t there, which is my unknown. My ay is 9.8 meters per second squared downward, so that's a negative sign. So when I plug into that equation, I get 0 is equal to 0 plus 30.1 meters per second times t plus 1/2 times minus 9.8 meters per second squared times t squared. Okay, so the zeros here out front aren't very interesting. And then I have this 1/2 times minus 9.8 times t squared. In order to solve for everything, I'm going to take this 1/2 minus 9.8 times t squared over to the other side of the equation. When I do that, I have to add it to both sides. So then that cancels out, and I end up with 30.1 meters per second times t is equal to 4.9 meters per second squared times t squared. I got 4.9 when I multiplied 1/2 times 9.8. The minus sign goes away when I take it to the other side of that equal sign. Now, in my next step, both my terms contain t. I have 30.1 times t is equal to 1/2 times 9.8 times t squared. I can cancel out one of those t's. I can divide t from both sides of my equation. When I do that, I end up with 30.1 is equal to 4.9 times t. Now I can solve pretty easily by dividing both sides by 4.9. And I end up with t is equal to 30.1 divided by 4.9. My units, of course, are going to be seconds. And so I end up with a time of flight of 6.14 seconds. Now that I have the time of flight, I can use that to find the range for the total horizontal distance traveled by this projectile. I'm going to plug into basically my only equation in the x direction. X is equal to x naught plus vx naught times t. Here, my initial position, x naught, was 0 because I put my origin there. Now I'm going to add on my initial velocity in the x direction, vx naught, which is 39.9 meters per second, and multiply that times the time of flight, which I saw for in the previous slide, and that's 6.14 seconds. When I multiply 39.9 times 6.14, I get 245 meters. So that's my range for my projectile. Finally, I want to solve for the maximum height of my projectile. To do this, I can't look at the total time of flight, okay? If I looked at the total time of flight, I'd be back on the ground. So what I really want is this point right here at the very top of my trajectory. And at that point, Vy is equal to 0. But I can't use the 6.14 seconds that I solved for earlier because that's where the projectile is over here lying on the ground. So I need to solve for a new time. and I need to know what the time is when it's at the top of its trajectory. To do that, if I know that the final velocity in y is 0 at the top, and I have the initial velocity in y, and I know the acceleration, then I can use the equation Vy is equal to Vy naught plus Ay times t. See, in that equation I have everything that I need except time, and so I can solve for that. So here, Vy is equal to 0, and that's equal to Vy naught, which is 30.1 meters per second, minus the acceleration in the y direction times the time, which is minus 9.8 meters per second squared times time. Now I can add that 9.8 times t to both sides, and I end up with 30.1 is equal to 9.8 times t. Then I can divide both sides by 9.8, and I end up with t is equal to 30.1 divided by 9.8. When I solve that, I get 3.07 seconds. Okay? If at any time you get a little confused by the algebra, just pause the video and make sure that you work it out on your own scratch of paper, right? And make sure that you get the same answer that I do after you go through that algebra. Now that I have the time, 3.07 seconds, I can use that time in another equation to solve for what the y position is at that time. The equation that I chose was y is equal to y naught plus Vy naught t plus 1/2 Ayt squared. So when I do that, I end up with y is equal to, that's what I'm solving for, y naught is 0, v naught y is 30.1, the time is 3.07 seconds, and of course the acceleration is negative 9.8. So here we go, 0 plus 30.1 meters per second times 3.07 seconds plus 1/2 times minus 9.8 meters per second squared times 3.07 seconds squared. When I plug all that into my calculator, I end up with the maximum height of the projectile being 46.2 meters. And that's it. Okay? Now, there's other ways that I could have solved this bit. Okay? Like I say in class, there's more than one way to skin a cat. So if you approach a problem in a slightly different way than I do, but you get the same answer, you're good to go. Okay? And that's fine. Alright, I'll see you in class when we'll work more examples together and we'll do more problems. See you next time.